Now, in this video, we're going to look at the Nobel Prize in Physics for the year 1903, won by Becquerel for his discovery of spontaneous radioactivity, and by the Curies for their joint researches on the radiation phenomena discovered by Professor Becquerel. First, some work and biographical work-related information, all coming from the official Nobel Prize site. You can always see the link to it on the bottom of the page, and first Becquerel and then both the Curies, and after that the summary of the awards-winning speech also from the official site. Becquerel then work. When Henri Becquerel investigated the newly discovered X-rays in 1896, for which Röntgen got the first Nobel Prize in Physics in 1901, it led to the studies of how uranium salts are affected by light. By accident, he discovered that uranium salts spontaneously emit a penetrating radiation that can be registered on a photographic plate. Further studies made it clear that this radiation was something new and not X-ray radiation. He had discovered a new phenomenon called radioactivity. That's some biographical information, work-related. Other information is skipped. These are quotes from the Nobel Prize. Becquerel's earliest work was concerned with the plane polarization of light, with the phenomena of phosphorescence, and with the absorption of light by crystals, his doctorate thesis. He also worked on the subject of terrestrial magnetism. In 1896, his previous work was overshadowed by his discovery of the phenomenon of natural radioactivity. Following a discussion with Henri Becquerel on the radiation which had recently been discovered by Röntgen, the X-rays, and which was accompanied by a type of phosphorescence in the vacuum tube, Becquerel decided to investigate whether there was any connection between X-rays and natural occurring phosphorescence. Phosphorescence is that when you put light on a substance, it also sends light and it keeps continuing sending that light even when you stop putting light on it from the outside. He had inherited from his father a supply of uranium salts with phosphorescence on exposure to light. When the salts were placed near to a photographic plate covered with opaque paste, the plate was discovered to be fogged. So there was some kind of radiation. The phenomenon was found to be common to all uranium salts studied and was concluded to be a property of the uranium atom. Later Becquerel showed that the rays emitted by uranium, which for a long time were named after the discoverer, Becquerel rays, caused gases to ionize, and that they differed from X-rays, and that they could not be deflected by electric or magnetic fields. For his discovery of spontaneous radioactivity, Becquerel was awarded half the Nobel Prize for Physics in 1903, the other half being given to Pierre Curie for the discovery of the Becquerel radiation. Here you see the prize winner experimenting with magnets. It seems to be a transformer in this laboratory. Then we go to Pierre Curie. The 1896 discovery of radioactivity by Henri Becquerel inspired Marie and Pierre Curie to further investigate this phenomenon. They examined many substances and minerals for signs of radioactivity. They found that the mineral pitchblende was more radioactive than uranium and concluded that it must contain other radioactive substances, new elements, radioactive elements. From it, they managed to extract two previously unknown elements, polonium and radium, both more radioactive than uranium. Then biographical information, also work-related, of course, other is skipped. Again, from the Nobel side, as always. Quotes again. In his earlier studies on crystallography, together with his brother Jacques, Curie discovered piezoelectric effects. That is, when you bend or deform a substance, it gives off electricity. Later, he advanced theories of symmetry with regard to certain physical phenomena and turned his attention to magnetism. He showed that magnetic properties of a given substance change at a certain temperature. This temperature is now known as the Curie point. To assist in his experiments, he constructed several delicate pieces of apparatus, balances, electrometers, piezoelectric crystals, etc., which were also used, of course, in his subsequent research. Curie's study of radioactive substances were made together with his wife, whom he married in 1895. They were achieved under condition of much hardships, very adequate laboratory facilities, and under stress of having to do much teaching in order to earn their livelihood. They announced the discovery of radium and polonium by fractionation of pitchblende, thus breaking it up, in 1898, and later they did much to elucidate the properties of uranium and its transformation products. Their work in this area formed the basis for much of the subsequent research in nuclear physics and chemistry. Together they were awarded half of the Nobel Prize for Physics in 1903 on account of the study into spontaneous radiation discovered by Becquerel, who was awarded the other half of the prize. Pierre Curie's work is recorded in numerous publications in the Compte Rendu de l'Académie des Sciences, dus the journal, the physique, and the annals, the physique et de chimie. So these are French scientific journals. Here you see the couple at work in their modest laboratory, as you can see. In relation to what we have now, this is all very primitive. But nevertheless, they did good work. Then Marie Curie, you see it's exactly the same as with Pierre Curie, so I'm going to skip this. Then biographical information related to her work. Again, quotes from the Nobel Prize site. Her early researches, together with her husband, were often performed under difficult conditions. Laboratory arrangements were poor, and both had to undertake much teaching to earn a livelihood. We already saw that. The discovery of radioactivity by Henri Becquerel in 1896 inspired Curie's in the brilliant researches and analysis. This led to the isolation of polonium, named after the country of Marie's birth, and radium. Madame Curie developed methods for the separation of radium from radioactive residues in sufficient quantities to allow for its characterization and a careful study of its properties, therapeutic properties in particular. Madame Curie, throughout her life, actively promoted the use of radium to alleviate suffering, and during World War I, assisted by her daughter Irene, she personally devoted herself to this remedial work. I think she was working with the ambulance services and in hospitals near the front. She retained her enthusiasm for science throughout her life and did much to establish a radioactivity laboratory in her native city. Madame Curie, quite dignified and unassuming, was held in high esteem and admiration by scientists throughout the world. She was a member of the Conseil de Physique Solvay, that's the physical Council of Survey, which held conferences from 1911 until her death. And since 1922, she had been a member of the Committee of Intellectual Cooperation of the League of Nations. Her work is recorded in numerous papers in scientific journals, and she is the author of researches on radioactive substances, translated from French, and isotopy and isotopic elements, and treatise on radioactivity. Here you see the couple again at work in the laboratory with much of the equipment created by themselves. Then we continue with a summary from the award ceremony speech by difficult Dr. H.R. Turnblad. The great discovery to which the Academy of Science resolved to award the Nobel Prize of 1903 for physics marks a stage in this brilliant expansion, while it is at the same time strictly linked to the discovery which won by the very first Nobel Prize of Physics. It's about the X-rays, eh? Further to the discovery of Roentgen rays, the question was raised whether they could not be produced in other conditions than those in which had been first observed. During the course of experiments in this field, Professor Henri Becquerel achieved results that not only contained an answer to this question, but led to a new discovery of the first order. When electricity is discharged from a tube filled with highly rarefied gas, the phenomenon of radiation occurs in this tube. This had been called cathode radiation. Negative radiation, is it? A negative charge. Which, when it meets an object, in its turn produces the rays discovered by Roentgen, X-rays. It often happens that these cathode rays also give rise to phenomena of light called fluorescence and phosphorescence. This, when you hit a substance with rays, like cathode rays, they give light, fluorescence, and when you stop, the light also stops. But sometimes the light continues for a while, and then it's called phosphorescence. In updates they encounter. Now this is circumstances which occasioned Becquerel's experiments. He asked himself if the bodies whence the phosphorescent rays emanate, after having been subjected for a longer or lesser time to the action of ordinary light, would not likewise emit Roentgen rays. To solve this problem, Becquerel made use of the well-known property of Roentgen rays to affect the photographic plate. And when these rays falls on such a plate, it darkens. Having placed aluminium foil upon a sensitive plate, he laid glass laminae on it with the phosphorescent materials that they were under study, contending that if the photographic plate was affected through the aluminium foil, this could only take place by means of rays which, like those of Roentgen, had the property of passing through metals, so it could not have been ordinary light or Roentgen rays or ultraviolet rays, for instance. Carrying his research further, Becquerel found that the sensitive plates bore images from certain substances, in particular from all the salts of uranium. He thus demonstrated that these substances emit rays of a special nature, distinct from ordinary light. This continued, and he established an even more extraordinary fact, namely, that this radiation is not in direct relation to the phenomenon of phosphorescence, that phosphorescent materials, as well as those which are not, can give rise to this radiation. That previous lighting is never necessary for the phenomenon to occur, and lastly, that the radiation in question continues with invariable force to all appearances, without its origin being traced to any of the known sources of energy. This was how Becquerel made the discovery of spontaneous radioactivity and the rays that bear his name, the Becquerel rays. Later they were split in alpha rays, beta rays, and gamma rays. This discovery revealed a new property of matter and a new source of energy, the latter of puzzling nature. Nobody had any idea where all that energy came from. As a result, if rays of this kind fall on an electroscope charged with electricity, it will discharge more or less quickly according to the greater or lesser activity of the rays, which make the air around the electroscope a conductor. The electroscope has thus to some extent played the same part in respect of radioactive materials as the spectroscope in search for new elements. Monsieur and Madame Curie, having thus found with the aid of the electroscope that the radioactive properties of the mineral pitchblende were more marked than those of uranium, stronger radiation, and came to the conclusion that pitchblende must contain one or more radioactive substances. By breaking up pitchblende into its chemical components and examining, again with the aid of the electroscope, the radioactivity of the products that were obtained, they at least managed by a series of solutions and precipitates to isolate the materials that were distinguished by a radioactivity of an extraordinary intensity, stronger than uranium and thorium, the only known substances at the time that were radioactive. Some idea of the prodigious work these results entail may be formed at the fact that it takes 1,000 kilograms of raw material to produce a few decigrams of these active substances. Of these, polonium was discovered by Monsieur and Madame Curie, and radium was also discovered by them in collaboration with Beaumont, and actinium by de Bierne. Of all these materials, at least radium has shown to be a simple substance. At the time, the others were not isolated yet. Becquerel had already shown by the study of radiation in uranium some of the most important properties of these rays. It was, however, only by means of the highly radioactive substances we have just mentioned, polonium and radium, that it became possible to carry out more comprehensive research into the Becquerel rays and in certain aspects to amend findings on them. Foremost among scientists who carry out this program, we find both Becquerel and also Monsieur and Madame Curie. Here we see the couple holding a specimen of radium. It's a drawn, maybe even a little caricaturic, but nevertheless. Becquerel radiation resembles light in several respects. Propagation is rectilinear, so it's in straight line. Like certain light wavelengths, it has a strong photochemical action, causes phosphorescence, etc. Yet it differs from light in certain essentials, for example by its property to pass through metals and many other opaque bodies. By the intensity with which it brings out the discharge of bodies charged with electricity, and lastly by the absence of phenomena of reflection, interference and refraction, characteristic of light. In this, the Becquerel rays are exactly similar to Roentgen rays and cathode rays. It has not been found all the same that Becquerel radiation is not homogeneous but is composed of different kinds of rays, some of which, like those of Roentgen, and later it was gamma rays called, are not affected by magnetics or electric forces, while others, like cathode rays, these are negative particles, electrons, like called beta rays, or Goldstein rays, which are positive particles, later called alpha particles or alpha rays. Like Roentgen rays, Becquerel rays have a very strong physiological effect. Thus, for instance, they attack the skin, affect the eye, etc. Lastly, certain of the radioactive substances have a special property which bears no direct relation to their beams. This is to make temporarily radioactive all the bodies in their neighborhood by producing a radioactive emanation which communicates the radioactive property to the surroundings. It is thus beyond doubt that Becquerel rays are in strict relation to Roentgen rays and cathode rays. The modern theory of electrons, which is used to explain this last form of radiation, has also been applied with the greatest success to explain the Becquerel rays. Later, Nobel Prizes will deal with this. We come to that in a few weeks. We could close our account of the discoveries of Becquerel and Curie at this point, as what we have covered is the main result of research they undertook early in 1903, and which is consequently to be considered in deciding the award of the Nobel Prize for 1903. Surely the discoveries we have outlined are important enough to deserve such a prize. These discoveries have taught us that special forms of radiation that were only known hitherto by electric discharges through rarefied gas are natural phenomena of wide occurrence. We have gained knowledge of a property of matter quite new to us, the capability of emitting spontaneously, as it seems, these marvelous rays. We have gained new methods infinitely superior in subtlety to any we have had in this sphere to examine under certain conditions the existence of matter in nature. Finally, we have found a new source of energy for which the full explanation is not yet forthcoming. That also will be the subject of many later Nobel Prizes. It will eventually give rise to new research of the very highest value in physics and in chemistry. The discoveries of Becquerel and Curie in their own right herald a new era in the history of the physical sciences. Now we can only touch on the magnificent experiment carried out in this domain last year by Curie, who discovered in radium the great spontaneous development of heat, together with the findings of Rutherford and Ramsay on the release of helium by radium, the alpha particles, discoveries that are bound to be of great importance for the physicists and for the chemists alike. The promise for the futures stemming from Becquerel's discovery seems near full realization. The discoveries and research of Becquerel and of Monsieur and Madame Curie are closely bound up with each other. The latter, of course, of co-workers. The Royal Academy of Sciences did not think it right to distinguish between these eminent scientists when it came to awarding the discovery of spontaneous radioactivity as a Nobel Prize. The Academy had thus deemed it equitable to share the Nobel Prize for 1903 by awarding one half to Professor Henri Becquerel for the discovery of spontaneous radioactivity and the other half to Professor and Madame Curie for great merit of which they have given proof in the work on rays first discovery by Henri Becquerel. As said, this comes from the Nobel Prize site. Ceremony speech is a summary. If you will read the complete speech, follow the link. And there's even more information on that Nobel Prize site. There's an article on Marie and Pierre Curie and the discovery of polonium and radium. You can also access it by following this link. I will also put all the links in the description under the video. And last, the beautiful Nobel Prize diploma received by the Curies in 1903. Always little works of arts. In the next video, we will deal with the Nobel Prize readings on the subject.